How are you doing today? Still some enthusiasm left for this lecture? Yes. Okay, good. So, as a reward in the beginning, I give you lecture notes. So, please distribute. But please don't have your heads buried in the lecture notes for the whole time, right? It's like if you are... I used to direct a choir once for 4 years, and it was always a bad thing to see people looking into the scores like this. Well, we were doing some serious music there, and... So don't do this. So bear with me here on stage. Okay, this is about enumeration in the space of triangulations. So essentially, this can be more or less two things. Either you do mathematics and you derive formulas for special point configurations, you derive bounds on the number of triangulations of a special point configurations, or you derive asymptotics. All of this has also been done. And let me give you some references, because this will not be the main topic here. So, formulas, or for the humanistically educated people, formulae, if you like. Bounds, asymptotics. Let me give you some references here. One that you know of is the famous number of triangulations of the n-gon. What kind of formula is that? Catalan number, and you pick your favorite. So this was lectures 1 and 2, right? But there has been more. We have seen a lot of theory about the secondary polytope. It had vertices corresponding to all regular triangulations of a point configuration. And since we know the normal fan of this, you can get bounds for the number of faces of this polytope by looking at corresponding hyperplane arrangements that go through all the faces of the secondary polytope. And in the paper of Bilera, Filiman, and Sturmfels on complexity of the secondary polytope, you can find bounds on this. So let me put this down. Bilera. Sturmfels. So it's essentially, I guess it's in the 90s. I don't know I think it's 91. And so this is bounds on sigma, a number of vertices of this guy. So there you have bounds on the number of regular triangulations. Essentially, you can think of this that the number of regular triangulations usually is a polynomial of degree in the codimension of the point configuration if the codimension is fixed. So then there are some nice new results by Günther Ziegler on triangulations of two-dimensional lattice point sets. So lattice rectangles. And I think he has recursion formulas up to like 4 layers of this kind of point configuration, right? So these are lattice points. And if you have not too many layers, then Günther can give you recursion formulas on this, how you can compute the number of triangulations. And the biggest recursion formulas are really recursions in more than one parameter. So then there is something, I guess, that Paco mentioned already, asymptotics on two-dimensional triangulations. And then there is also by Paco some recursion formula on the codimension 4 cyclic polytope, and also on products of the two simplex with any other simplex. So and there is more, right? Just as examples, if you want to look that up, then all of these papers are very interesting. This is just a preprint by now. You probably have to contact Günther directly to get a copy. Okay, but there is also another way to do it. So this is like the smart way of doing it. You get a formula, and then you know the number, and you derive the formula from the structure of your point configuration. But sometimes you don't see a way to do this. And so as an act of desperation, you resort to computer calculation, right? And computer calculation is kind of standard in dimension 2. What I mean is in general dimension. Okay? So there also have been some results on this. So in Jesus' thesis, he uses a maple code called puntos to find several non-regular triangulations, for example, of the 4-cube and of products of simplices that have not been known before. And so this is maybe the grandfather of all computer codes in this area. And so I myself, I had a code, HST, that was for enumerating triangulations of C and D in general. And from this, I started out to write a program that is now distributed under the name TOPCOM, which enumerates triangulations in any dimension of any point configuration with rational coordinates, let's say. So you cannot input any irrational coordinates. You cannot have coordinates like square root of 2. If you put in a floating point approximation of square root of 2, then I will take that seriously and think of that as a rational number. Okay. So actually there has also been done some work in the group of Imai, but these codes, so on enumerating regular triangulations and also all triangulations, but the codes are not distributed officially. That means if you go to the website, at least as of yesterday, you cannot find any code there. Although probably if you contact the people at Imai's group, you probably get a code. So anyway, we now will deal with things that are implemented in TOPCOM. And let me list some tasks here that I would like to talk about later, because we need some preparations for this. So tasks here are what? First of all, if somebody gives you a set of d-dimensional simplices and you have your point configuration, you want to know whether this is a triangulation or not. So this is the kind of the basic functionality that you would like to have. If you have something in your hand, check whether this is a triangulation. So check the triangulation properties. So once you can do that, this doesn't give you yet a tool for computing a triangulation. So what you would like to do is actually compute one. So find one triangulation. Next, if you have one triangulation and you know how to find flips, then you have the graph of all triangulations, and you might want to explore a component of that graph. So find or enumerate a component of the flip graph. But as Paco has told you on Monday, I guess, there are point configurations that don't have a connected flip graph. So if you just explore a component of the flip graph, you don't get all triangulations, right? So you really want to have an algorithm that gives you all triangulations. So these are the 4 basic tasks that you may want to deal with if you want to enumerate triangulations in the computer. Okay. Now let me come to some issues here.
Is there any application also for the number of triangulations?
You mean if you have the number, then what?
Yeah.
Something like that. Yeah, for example, you will hear something in the lecture of Bernd Sturmfels tomorrow, that the number of regular triangulations has something to do with the number of Gröbner bases. Actually, it's a lower bound for certain ideals, certain binomial ideals. Actually, you can identify the regular triangulations with the possible radicals of Gröbner bases of a certain binomial ideal. This binomial ideal is in a natural way related to the integer kernel of your matrix A, because it has, if you have an element in the integer kernel, you take just as a positive monomial the positive coordinates as powers, and if you have negative coordinates in your integer kernel vector, you take the negative coordinates as positive powers of the negative monomial in your binomial, and that gives you a binomial idea, and the Gröbner basis of this, if you look at the radical, that corresponds to exactly one regular triangulation. If your matrix A happens to be unimodular, then the number of triangulations is exactly the number of Gröbner bases that you can get from differing the term orders. So this would be one thing that is interesting about this. On the other hand, enumerating triangulations, regular triangulations have a lot to do with algebraic geometry, stored varieties, and non-regular ones don't seem to have so many connections to that. And sometimes people would like to know whether if you just pick any triangulation in the set of all triangulations, can you expect that to be regular or non-regular? So are there asymptotically more regular ones or more non-regular ones? And this is also a branch of research that is investigated. And of course, in computer calculations, you want to get an idea what the trend is, right? It's like a poll on the number of triangulations for special examples. And of course, there are spaces of triangulations, like the ones of cubes, that are still a mystery. So the structure of the graph of triangulations of cubes in general dimension is not well understood so far. So one thing you would like to investigate first is how does the number of triangulations grow? Is there, if you have this, if you explore the graph of triangulations, then of course you get also information on the flip neighborhood and things like that. So you want to study all these things by looking at examples, right? And for this you would like to know the numbers, but maybe there are also other impressive applications of that. Of course, if you can enumerate, I mean, the Catalan number is one example. I mean, this doesn't just enumerate the triangulations of the n-gon, it also enumerates the number of binary trees and so on, right? Okay, so I would like to talk now about some issues. We don't want to have a general position assumption in our setting, because, for example, we would like to compute the number of triangulations of cubes, or at least the number of triangulations in a component of the flip graph. But the cube is highly degenerate. It's not in a general position. It has a lot of coplanarities, right? And if we just say we are writing computer codes for just enumerating triangulations in general position, that doesn't get you anywhere for interesting polytopes, right? Because you just get simplicial polytopes that way. So we don't want We don't want a general position assumption. So this makes it very much different from computational geometry standard code, right? So there exists a lot of very smart computational geometry codes, but many of them just assume general position, or they don't care. I mean, the triangulations are to model shapes in a way, and it doesn't matter whether the triangulation points are in general position or not. It's even better if they are in general position. So, but we don't want to have that because we are after structural information. And what does this mean? I mean, if 4 points are coplanar in R3, and I want to keep track of that, if I do just calculation in, let's say, double arithmetic, then I have absolutely no feeling of what should I consider coplanar, right? If this is not really exact coplanar, then I have to deal with things like I consider a certain epsilon below 10 to the minus 6 as 0 or something like that. If I compute the determinant and its absolute value is at most epsilon, then I say, well, this is coplanar. But it might be not the case. I mean, I can construct polytopes that have arbitrarily small non-zero volume simplices in them, right? So the stability of calculation suffers, of course. Okay, second one. In the conditions of what is a triangulation, you see that the two simplices have to intersect in a common face. So if you just go about this naively, then what does this mean? You could just think of your simplices as defined by their facets, and you take the facet defining hyperplanes, like this. So like this is one simplex. And you think of this as the intersection of these half spaces, right? And if you then want to compute the intersection of this with another simplex, then naively what you have to do is to add together the whole set of inequalities defining the two simplices, right? So the simplices are on the respective positive sides of these hyperplanes. And now what you see, the intersection is this, because this is on the positive side of every hyperplane that you have, right? So that means intersection. So intersections of simplices appear in the triangulation properties. So the characterizing properties. And that means, in general, if you go about this naively, you have to compute linear programming problems in order to find the intersection of two simplices. So and I mean, you can use your favorite linear programming code, but there are not many available that will do this for you in exact arithmetics. So if you have rational coordinates of your simplex, then you first have to find out what the inequalities, defining inequalities of that simplex are. Then you have to concatenate, and then you have to look whether this has an interior point in order to find out whether these simplices intersect in their relative interiors. And there is a code by Komei Fukuda, CDD, that does this for you in exact arithmetics, but it takes some time to compute the intersection of simplices. And now what do you need? You need the intersection of every pair of simplices to just check one triangulation. So this is a certain problem if you compute in the coordinates of the points all the time. And then we have this coverage property. Triangulation properties contain the convex Hull operations. And again, convex hull operations are pretty much time-consuming, and not many codes exist with exact arithmetics, except for CDD maybe. So same thing. While I am writing this, you may get an idea what is the cure for all this. What do you think? And look here and not in the lecture notes. Right? I told you something on Friday, right? In the cyclic polytope lecture, I told you a certain characterization of triangulations. And it didn't contain any of these two, right?
Oh, using that abstract definition?
Yeah, it is just a combinatorial characterization of what a triangulation is. And the general idea now is we don't want to fiddle around with coordinates all the time in our code. We just want to do it, let's say, once. And after that, we want to have purely combinatorial calculations. So we want to do some calculations with the coordinates because that's the input, okay? And then after we have done this, we want to have purely combinatorial calculations. So So that's the idea. And that means once we have computed our combinatorial structure that we are using for these purely combinatorial calculations, we never touch the coordinates again. So and if we make any mistake in the beginning, then we still can make sure that this is a correct calculation. This I don't want to discuss here because that means we have to check consistency of a certain combinatorial structure. So I will assume that we don't do any mistake here. And this is easy because this is just about calculating determinants. So let me put this here already. Calculations with coordinates are reduced to computing determinants. And determinants, to calculate determinants, is certainly much nicer than to compute interior points of linear programs or convex hulls. Okay, so, and what kind of determinants are this? You haven't seen determinants in the definitions and in the characterization of triangulations, but we will link that in a minute. But first of all, let me introduce to you the main actor of today in a way, because there is a special map that allows us to do all things that we would like to do today in a combinatorial way. So many things you will see today are not new to you probably as such, but just the way how you can do it in combinatorial calculus may be new to you, right? Okay, definition. So let A be a d-dimensional point configuration so there's nothing special about point configuration here. As usual, you can use homogeneous coordinates, and what you get is somehow a pointed vector configuration. But you can also generalize this to vector configurations that are not necessarily pointed. But I don't write that down here. It's just the same thing. So point configuration in R to the D, and let me use again the shorthand notation R is D plus 1, which is called the rank. That would be the dimension of the corresponding vector configuration if I add ones in the last row of every vector. And then the chirotope of A is the following map. It is denoted by chi of A sub A, like chirotope, or chi, if you like to pronounce this European way, like chirotope in Europe. So is a map that maps any R tuple of points from 1 to n corresponding to the labels of our point configuration. So let me put here n is the number of points in A. To what? It's either minus 0 or plus minus 1 plus 1, but this is usually abbreviated like this. And any R tuple of labels here goes to the sign of the determinant of the corresponding points. A1, 1, AIR, 1. So does this make sense? R is D plus 1. So we have D plus 1 rows because we have D coordinates for every point and 1 extra. And we have D plus 1 columns, so this might make sense. And this gives us a map. So these are just the homogeneous coordinates of these AIJs. So we have already had another name for this that is used in computational geometry, order type of A. Okay, let's make a little example here. So this will be the determinant calculations that we need. Let's look in dimension 1. So we have points like this, let's say. And let's say no two of them are equal. 1, 2, 3, 4, 5. And it's easy to see that the sign of the determinant is plus if and only if I is smaller or equal to j. But anyway, actually, if you have a chirotope that just differs by another chirotope by taking minus where the other one has pluses and keeping the zeros, then this doesn't change much. You just choose one let's say, one reference orientation of a set of D plus 1 points, and then you are set. But this is just, if the standard basis is plus, then this holds. Dimension 2, we just look at foregone again. Okay. So what we already know is that if we go like this, so we make, for a triangle, we look at the consecutive labels, and then we draw something like this, right, along the labels. So, and if we agree on that this is plus, and if you calculate with the standard basis here, then this will be plus, then also this is plus, and this gives you that, for example, you get a plus here if, for example, ij and k are ordered in this way, then you get a plus here. But you can also list some others. Anyway, you can make the following observation here. What happens if I just put here chi of, let me put an example here. 1, 2, 3 is plus. What is chi of 1, 3, 2? Without calculating. Minus. You just go the other way around, right? But there's another way to see this. I mean, here you have the picture, and that's fine to see it like this. What did you do with 2 of the labels? You swap 2. What does it mean in the determinant? You just swap 2 adjacent columns. That means you get a minus there. And so that means that chi is determined on I1, I2, and so on, IR, with I1 smaller than I2 smaller than IR. So you need not really compute more than this, right? Because everything else is either you have 2 elements that are equal. I mean, what is chi of 1, 1, 3, let's say? 0. You know from the alternating property of determinants immediately that if 2 columns are equal, then the determinant must be 0. Okay. So now on Friday we had a combinatorial characterization of triangulations that had just circuits and facets in it. And I would like to recall that one here. Let me put it here. So, I'll give you a short preview of how we can carry out the combinatorial calculations. So, the theorem of Friday is the following. A subset, so T is a subset of D plus 1 subsets of A, T not empty, and this thing is a triangulation of A if and only if, so A in R to the D full dimensional, let's say, if and only if 2 properties are satisfied. IP was the one that every pair of simplices intersects, and this didn't have convex Hull operators in it anymore. It was for all sigma, sigma prime in T, there is no circuit C plus C minus with C plus completely contained in sigma and C minus completely contained in sigma prime. So this was the minimal obstructions for bad intersections. And UP was the following. Every interior facet of a simplex interior means interior in the convex hull of A, of a sigma in T, must be contained in another simplex. Sigma prime in T, and sigma prime is not the same as sigma. So that's what I mean by another. Now, you may see that this is purely combinatorial, because once we have the list of all circuits, then we can check this without drawing on the coordinates again, right? You just look for bad circuits in the simplices. So no coordinates involved. So this can be checked purely combinatorially. For IP, this is clear. Only combinatorial data that I've used there. But for UP, this may be not so clear at first glance. So, but what would you think is the combinatorial structure that gives you information on this? You need something about interior in A, facet of a sigma in T, and must be contained in another simplex. So something must be contained in another simplex of T is a combinatorial condition. You just look for another simplex that contains this one, so no coordinates involved. But how do you get interior facet of A? So if this is A, and this is a simplex in A, let's see, let's remove this one to have, then how can you find out which facets of this one are interior to A? Give me a keyword. What structure might be helpful here? What combinatorial structure? The link of the simplex is empty because this big simplex is full dimensional, so there's no link. Very similar to this one. So these were the circuits. So what is this then? It must be something else. So what else do you know as a combinatorial structure? Co-circuits. And what would you think is the condition? If I have a facet, what does it induce? It is D points. They span what? A hyperplane. So let me look at this facet. It spans a hyperplane, right? This gives me a signature, a co-circuit signature. So this point is plus, and these points are minus, let's say. And these points are 0. So why is this an interior facet? Plus and minuses, right? So it must cut through the point configuration. It has points on one side and points on the other side. Okay? So then it's easy. If you look at this thing here and the corresponding signature here, you have, let's say, just pluses here. Okay? Everything is plus. So this is a facet that supports the polytope spanned by the point configuration. That means its intersection with the convex hull of the point configuration is a facet of that point configuration. That means that the spanning facet of that simplex is at least contained in a facet. And that means it is not interior. So the circuits help here. Co-circuits help here. So the co-circuits of a facet of this is sometimes used as a facet. It's smaller in the phase pole set of the sigma. Co-circuits of this tau, let's say positive, that means just pluses and zeros, then not interior. Tau not interior. Mixed, let me call this mixed interior. That means we have a combinatorial characterization of triangulations, and that means we could check a triangulation if we could compute this list of circuits and co-circuits, right? So this is one thing. And the second thing is let me remove this right away. We can do it so IP and UP can be checked by computing determinants. And determinants of square submatrices of A with a 1 in the last row. Let me put it like this. And there are at most n choose d plus 1 many. Okay. So, and the remark is, this is much nicer. So it's much easier to do in exact arithmetics than linear programming or convex huls. Essentially, there is also theoretically an algorithm that computes the determinant in polynomial time in exact arithmetics. If you work in fields with finite characteristics and you just increase that characteristic, there's a way to do it so that your coefficients in your calculation will not grow too much. So you can do it. Theoretically and also practically, it's very fast. So. And in linear programming, I don't know of any algorithm that runs in polynomial time that gives you an exact result on a polytope. So there are polynomial time algorithms for linear programming, but they are just algorithms that give you epsilon feasibility or epsilon optimality. That means you choose epsilon and the algorithm will give you something that is in up to epsilon optimal or up to epsilon feasible. Same thing, I guess, for convex hull calculations, but I'm not sure about that at the moment. So, and if A is rational, okay, in exact arithmetics, if A is rational, so. Okay, now we have this here, which is good because it allows us to compute everything combinatorially. And we have this here, which says that this can be done by computing determinants. And this is the one that I would like to discuss a little bit more in detail. So I guess the determinant calculation is easy to find. It's the chirotope. And what we have to do is find out how the chirotope helps us to find co-circuits and circuits. Is that right? Good. Let's start out with the easier one of the two, which is the co-circuits and the chirotope. By the way, why is it plausible at all that this has to do with determinants? Why do co-circuits have anything to do with determinants? Or why is this a close connection?
How do you obtain that chirotope using the just combinatorial structure?
I have to compute in the beginning the determinants, which is not combinatorially available.
Yeah, so determinant still has some problem with the arithmetic or something?
Yeah, I have to use an exact calculation for the sign of a determinant. Actually, I don't even need to calculate the determinant. I just need to calculate the sign of the determinant, which is at least theoretically easier than computing the determinant. And there are algorithms. If you Google, just look for sign of determinant, algorithm, complexity, something like that, then you will see that there are algorithms that run pretty fast computing the sign of a determinant. You can pick your favorite algorithm for doing this. They give you the exact answer if you give the exact input. So you have, and that's why I said rational. So the input should be also exact, of course. So you pick your favorite algorithm for computing the sign of a determinant, and there are some available. Actually, what I implemented in TOPCOM is just using Gaussian elimination with exact arithmetics, and for most coordinates that would allow you to compute anything about triangulations afterwards, this works just fine, right?
But, for example, if you have some square root of 2 or something like this, then the Gaussian elimination does not work for that one. How do you want to?
Then this doesn't work in the field of rationals, but it works in other fields maybe, if you extend the field by a square root of 2. And then this is entering the field of symbolic computation, right? So you have a symbol like square root of 2, and then you proceed by keeping that symbol, as you would do on a piece of paper, right? Okay. Let's proceed with co-circuits and the chirotope. Let me give you the proposition that gives you the connection. Assume, let me denote C bar star in a subset of A spans D minus 1 dimensional hyperplane. In R to the D. Then this will give us a co-circuit signature that looks like this. Then C star, considered as a map that assigns to every label of our point configuration a sign like this. And this is sometimes called a sign vector. So by this, you immediately get a new way to write down co-circuits and circuits. Every I goes to the chi of C star bar, comma, I, right? And you need a fixed, with a fixed order on C star bar. So, and this is then with, you can put the positive part like this. This is then the set of all I such that I in N such that C star of I is plus and C minus star is the set of all I in N such that C star is of I is minus. So this is the positive part of this. This is a negative part, and what I claim is this is a co-circuit signature. On C star, because C star contains all the elements that possibly are non-zero, right? So actually, the opposite signature is also a co-circuit signature, but I won't mention that here explicitly. So what are you doing? You just evaluate chi on the columns corresponding to the points that span the hyperplane and on one other point. So, for example, if this point is one of these, what happens? 0 immediately, right? 2 columns are equal. So this corresponds to that this point is also on that hyperplane, which is clear because it's one among these points that span the hyperplane. But if it is also on that hyperplane, although not among these points, then this will be also 0, because then you can see this, the simplex spanned by these d+1 points is then flat. It's coplanar, so its volume is 0, so the determinant must be 0. Okay? So examples for d equals 1. Let me just put now another set of points here. It's 1, 2, 3, 4, 5. Like this. And let's take C star is just the point 3 as an example. So that means we are in dimension 1, so a hyperplane has dimension 0, so it is just 1 point, spanned by 1 point. I take 3 now, and then let's just check what the cocircuit signature given by this proposition is. Okay, C star of 1 is corresponding to the formula 3, 1, and this is minus chi of 1, 3, and so this is minus. Okay? C star of 2 is chi of 2, 3, 2. So this is again minus, right, by the same consideration. C star of 3 is chi of 3, 3 is 0 by the considerations we had already. C star of 4 is chi of 3, 4 is what? So 4 is here. So if I pick this hyperplane here, what is the determinant 3, the point 3, and the point 4, and both the 1 and they have the same coordinate, right? So what do you have in the determinant? 2 equal columns, right? So it's 0. Last one is chi of 3, 5. So that's something that we had in our example for the chirotope already. It has to be plus. So that means we have a cocircuit that has C star plus is just 5, and C star minus is 1 and 2, right? Now, do you see that cocircuit? I mean, you see it, right? So it's, if you go to the right, then you have plus from here, and the other side of this hyperplane is minus. So it coincides with our definition of what a cocircuit signature should be. There should be a hyperplane such that one side is plus and the other side is minus, and all points on the hyperplane are 0. So this definition coincides with what we had already. Okay. And I skipped that two-dimensional example because I do that. I'd probably skip the next slide rather than this one. Two-dimensional example, again, the foregone. 1, 2, 3, 4. And maybe the middle point, yeah. Like the one in the exercises about the Gale diagrams, Gale transforms. So these should be collinear. And let me choose C star bar as, what did I choose? 1, 5. So then C star of 1 is, according to the definition, chi of 1, 5, 1 is 0. C star of 2 is chi of 1, 5, 2 is. So we just look it up in the picture because it's easier like this. So it's 1, 5, 2. 1, 5, 2. So it's like this. Okay? See this? And this was minus. You could also swap 5 and 2, and then you get a plus. And that means this must be minus. C star of 3 is chi of what? 1, 5, 3. But what is this? 0, exactly. And C star of 4 is chi of 1, 5, 4. This is what? 1, 5, 4. Which one? Plus, right. Is it? Yeah. Plus. And then finally, C star 5 is chi of 1, 5. 5 is 0 by what we already had. So this gives us the list. C star plus is just 4, and C minus is just 2. Okay, and now what did we start out from? That was 1, 5. So we took 1, 5, looked at the hyperplane spanned by this, and did this calculation. And what you see is, well, the positive side here. No, 2 is the negative side, and this is the positive side of it. So it's exactly that. So this is no surprise. If you have a fixed order on something on that hyperplane, then if you add at a final vertex something on this side, then it will have another orientation than the one on the other side, right? So you see the definition right away, in dimension 2 at least. And in general, you can describe the hyperplane spanned by these elements easily by a determinantal equation. Let me do this here. So hyperplane equations and determinants. And the corresponding proposition is the hyperplane spanned by the affinely independent points AI1, AI2, AID in RD is the set of all x in R to the D such that the determinant of AI1, AI2, and so on, AID with 1 in the last row, plus x with the 1 in the last row is 0. And without loss of generality, you can sort I1 up to ID. So, and this is a linear functional in X, because the determinant is multilinear, right? So it is In particular, it's linear in the last column. And that means we got the equation of the hyperplane spanned by these points, and that means we can just look it up where it is positive, where it is negative, and where it is 0, because that's exactly the sides of the hyperplane. So moreover, sign determined AI1, AI2, AID X. Let me put here an AI for the variable sign that determines co-circuit, the corresponding co-circuit signature. And you see, this is exactly the definition of our chirotope, right? So from this proposition, that proposition follows. So you have to be careful, though. What we have seen is C star can have more than these d zeros. What did I write here? N minus d, that is not, it should be d, right? I have d points spanning the hyperplane, so those d points will be 0 anyway, but there might be more. So more than d zeros. So please make a d out of the n minus d. So, okay, and positive co-circuits correspond to facets of the convex hull. That's something we've already mentioned. Okay, you see how we can get the co-circuits from the chirotope? It's pretty easy because, after all, the equations of all those hyperplanes are just determinants. Right? While I am erasing these blackboards, you might think about what circuits have at all to do with determinants. From the definition of circuit, you may have an idea. So maybe you don't find the correspondence, but maybe you find at least the reason why this may work. Okay, so but then you have to have some formula for the chirotope in the Gale transform. You can do that. Actually, it exists. It's not so complicated, and you can do it. I will do it in the primal picture because you can see it, and you can actually memorize it, how it goes, and once you know that once and forever, then you can reconstruct everything easily. But what is a circuit? Remember what a circuit is by definition. Minimal affine dependence. What is a minimal affine dependence? It's an affine relation among the points, right? If you add ones in the last coordinate, then it's a linear relation among the points. But what is a linear relation? When this linear term equals this linear term. It's what? How can you find out the coefficients of an affine relation or a linear relation? How would you do that? Right. Find a kernel element. How do you do that?
Theoretically, you use Penrose law. I don't think it's the best way to press that.
Yeah, that is one possibility. So you just solve a linear system of equations, right? And if this happens to be a linear system of equations that has a square coefficient matrix, then you could possibly use Cramer's rule. And what is in Cramer's rule? Determinants, right? There you are. So it's like Pascal's triangles. Determinants appear everywhere, right? So, and what you get out of this is the following proposition. Let me copy this so I'm consistent. So let C be a set I1 smaller than I2 and so on. Now the order is essential because we will have an alternating sign in our formula of d plus 1 points in A. Then we will now write the circuit signature of these d plus 2 points also as a sign vector, right? So it is a map of every point to minus 0 plus, and ij, one of these, goes to what? It goes to 1 to the minus j times chi of, now what do we have to do? We have d plus 2 points here. So in order to be able to compute the chirotope value, we have to get rid of 1 point. So now you take your C, and which point do you get rid of? I mean, there's an obvious choice. It's the ij, right? Okay, this is just one thing, and all the rest doesn't take part in that affine dependence, so it goes to 0 if I is not in C. So here we have ij is in C. So, statement still missing. Then this is a circuit signature. On C. The opposite circuit is also a certain signature. Okay, this looks a little bit more complicated, but actually it's not too hard. Example, same example as before. 1, 2, 3, 4, 5. Okay, now what do we choose for C? Let's take, we are in dimension 1, so 1 plus 2 is 3. We need 3 points to span an affine dependence. So let's just take 2, 3, 4 to have the features here. So then, C of 1 is what? We have to add the minus 1 to, well, it's 0 because it's not in that set. Yeah, I mean, nothing to calculate. C of 2. Now, 2 is the first in this set. So we have minus 1 to the 1 times chi of 2, 3, 4 minus the 2. So it's chi of this. This one is a plus, this one is a minus, so this one gives a minus. Okay? Oh, sorry, this is 0, then it is 0. This is 0, right. Yeah, the interesting case. That was the interesting case. C of 3 is also in here. That's minus 1 to the 2 times chi of 2, 4 is what? This is plus. This is minus 1 squared is also plus, so this is plus. C of 4 is minus 1 to the 3 times chi of 2, 3, 4 minus 4. So chi of 2, 3 is positive, so this is negative. This will give you a minus. And C of 5, again, is 0, more or less by definition. So if we look at this set, 2, 3, 4, then on this set, we have the signature 0 on 2. So this doesn't take part. And then one of these is positive, the other one is negative. And it doesn't matter much which one. 3 was a positive one, 4 was a negative one. So this one's positive, and this one's negative. And this pretty much looks like correct, right? So you have this plus minus this gives 0, okay? So very good. Another example. Dimension 2. So let's take C as 1, 2, 3, 4. And then C of 1 is minus 1 to 1 times chi of 2, 3, 4. 2, 3, 4 goes counterclockwise. We have agreed that this is positive in our case. So negative times positive gives negative. C of 2 is minus 1 to the 2 times chi of, well, you see the pattern, right? What will happen? I mean, all these will just be an ordered 4 tuple of points with one removed. So it will remain an ordered 4 tuple of points. All these orderings give you counterclockwise orientation. So what you will keep is this alternating sign. So this will plus, and C of 3 without further calculation must be minus, and C of 4 must be plus, and C of 5, of course, must be 0. And again, we see that a minus on 1 and a minus on 3 and a plus on 4 and a plus on 2 is what we know what a circuit looks like in this picture, right? Okay. Now let me give you a little proof of this rule. Proof that this formula gives a circuit signature. So we assume homogeneous coordinates. For the AIs in A, and now we start out with such a C. Let's C in A be an affine dependence such that it contains D plus 2 elements. And now I'm not requiring that this C is a minimal affine dependence because I couldn't calculate the formula. If I start out with a minimal affine dependent set, then I would not know how to use the chirotope for finding out the circuit signature. So I start out with D plus 2 points, and then I know for sure it must contain a circuit because this set is affinely dependent. And now the idea of the system of equations is this. You know that this is an affine dependence, meaning that this is 0, And this is the same as writing one of these terms on the putting one of these terms on the other side. So in a way, we try to make modifications on this affine dependence such that we see features of our formula, right? So now we have one feature of our formula already, which is we have C minus J somehow here. Okay, now we consider this here fixed, a fixed coefficient. So, because if we multiply everything by a common real number, then this will stay true, right? So it doesn't matter much. So we can just fix 1. We could fix it to 1 or plus 1, minus 1, whatever. I just fix it. So consider lambda j fixed. And these are now considered variables. And so if you look at this, how many variables do you have here? It's just d plus 1, right? And how many equations do you have? How many scalar equations, I should ask, are this? I mean, this is a vector with how many numbers? D plus 1, homogeneous coordinates, okay? So d plus 1. D plus 1 equations for d plus 1 variables. Okay, and this makes this coefficient matrix quadratic. Okay, so we can apply Cramer's rule. So that means and this gives us what? So we now solve for lambda I. Yeah? Lambda j is fixed. And now we can solve for every lambda I with I not equal to j. And the rule says we have to divide the determinant. I need some notation for this. And I explain this in a minute. It has A1 here. And then it doesn't have AI in this place. So I put a hat on AI. Maybe the topologist will like that because this just means this is missing. And in topology, usually, if you put a hat on something, then this means that is missing in simplices. Okay, then at some point, we have AJ, which is also missing, and AD plus 2. So this here is the determinant where you remove column I from this coefficient matrix. But this coefficient matrix doesn't contain J anyway, right? It contains instead, no, it doesn't contain J, right? So you have to have like minus lambda J, AJ here. So, and the bottom you have A1, AI is there, and AJ is missing, AD plus 2. So you can sort it out. This is Cramer's rule. If you have in the denominator, you have these columns, which are all except for AJ. And in the numerator, you have this as a column, and you have this in the place of AI here. So you can put it other ways. So then you have minus 1 to something, maybe, and then you have some reordering of this. So take this as a black box, okay? This is the rule. And then what are you doing? First of all, you use the linearity. So you, of determinants, minus lambda j goes out of this determinant. A1 to AJ. AJ is now in the place of AI only. And then there is the original column of AJ where AJ is missing. So it's like this. And then down here, you have the determinant of A1, AI, and AJ missing. So now you have to just observe. We would like to get this in the place of its original position. So we want to swap this over here. Okay? Then we have like AI missing here. This is in the i's position now, but we want to have it in the j's position. And if you do the count right, then this requires exactly j minus I minus 1 swap operations. You just sort it out. You can usually you never know whether it's j minus I or j minus I minus 1, and that you find out by adjacent swap. If position j and position I are adjacent, then you don't have to swap at all, right? So what does it give you? It gives you that this is lambda j times minus 1 to the j minus I minus 1 times these determinants. Determinant of A1, just AI missing now, AD plus 2, divided by the determinant of A1, just AJ missing, AD plus 2. Okay. Now this is, lambda I is this. But now we are not interested in the exact values of lambda I. What we are interested in is how these things separate into positive and negative coefficients, right? So how can we find out? We just take this as a reference point. Lambda j is a reference point. How can we find out what sign lambda I has with respect to lambda j? We just divide lambda I by lambda j, right? So this gives you lambda I divided by lambda j is, if you sort it out correctly, minus 1. So we get rid of the minus. That takes care of the minus 1 here. Then we have minus 1 to the j minus I is the same as this. And then we have, in shorthand notation, c minus j and c minus I here. So, and that means these two guys have the same sign if these two things have the same sign, right? And this is exactly how you got the circuit signature from the formula, right? You took the position of the coefficient and multiplied by the chirotope of the dependent set minus that element. So this is nice, right? Isn't it? So chirotope determines the circuits and determines the co-circuits. And there is a definition of something that we already mentioned in this course a number of times, which is the oriented matroid of A. And this is not the whole story about oriented matroids, but at least I give you a definition what the oriented matroid of A is. What would you think the oriented matroid of A is? What kind of data would determine the oriented matroid? It's a combinatorial structure that gives you the circuits, the co-circuits, the chirotope, whatever. So I would like to define it like this. The oriented matroid of A is the equivalence class of all point configurations having the same combinatorial data, right? So that means in particular with A prime has the same number of elements. The dimension of A prime is the dimension of A. Then the circuits of A prime are in a way isomorphic to the circuits of A. The co-circuits of A prime are isomorphic to the co-circuits of A, and chi A prime is isomorphic to chi A. And these three things mean isomorphism induced by label bijection. Of course, this with 1, 2, 3, 4, 5, and this with 1, 2, 3, 4, 5 should be in the same equivalence class, right? So we say these two things have the same oriented matroid, meaning they have the same equivalence class with respect to this set of data. And you can do the label bijection, and this will induce some bijection, some isomorphism on circuits, co-circuits, and the chirotope. Yeah?
Yeah, when you talk about dimension of A prime, dimension of A, you mean dimension of the convex of?
Yeah, that's right. Yeah, dimension of a point configuration is dimension of its affine span. That's the well-defined term. Okay, this is something that is very often used in sloppily. So people say the triangulations only depend on the oriented matroid of a point configuration. This is something that you now know. It doesn't depend on the special coordinates. It depends on the circuits and the co-circuits, because we had a characterization of triangulations in terms of co-circuits and circuits, meaning that triangulations only depend on the equivalence class, right? And this is what we mean if we say the triangulations, set of triangulations only depends on the oriented matroid. And the oriented matroid now is the data structure that we use currently for calculating triangulations. We compute triangulations by just using these structures. And actually, if you are doing it in a more efficient way, you will use just this. And this is overdefined, right? So if this is isomorphic, then this will be isomorphic automatically, and these also. But so sometimes people speak about circuits, sometimes about co-circuits, sometimes about whatever. And let me just read the remark to you that the oriented matroid of point configurations are just the tip of the iceberg. So there is an axiomatic system of what a set of circuits in a set 1 to n must look like to be a set of circuits. It has some axioms to it. Same thing for co-circuits, same thing for chirotopes, and same thing for vectors, covectors, topes, and you name it. And this gives things that are not the oriented matroids of any point configuration, so-called non-realizable oriented matroids. And this is a whole new story that we are not going to talk about here. Maybe Paco on the last day, I don't know. Maybe a little bit. So yeah, that's what I wanted to say this morning. And this afternoon, we will have some hands-on check out how that works in the computer. Okay? So any questions to this? Then one other announcement. David wants to take a photo of all of us in front of the building. So that would be nice. So please, right now, go out of this building and wait in front of the front door. Thank you very much.